What we have discussed so far involve only static or non-moving fluid. Discussion on physics of moving fluid or fluid dynamics could go really complicated. Nonetheless, if we limit our discussion only to ideal fluid situation, then it isn't so bad. We are able to derive some important concepts which are the objective of this lesson. Now, what do I mean by a fluid being ideal? Well, two things are required for a fluid to be called ideal. One, it is incompressible, meaning it cannot be compressed and hence its density remains constant. Realistically speaking, all fluids are compressible to some extent. But well, if you have a highly viscous or in layman term highly thick liquid such as honey, it can be treated as an ideal fluid. The second condition is it flows in laminar manner. By laminar, it means that the molecules that form the fluid body flows in such a way that their paths do not cross one another as shown in the picture here. When a laminar flow encounters an obstruction, it will flow around the obstruction tidally as shown here, without cutting its other path. As a result, it may create pockets of vacuum around the obstruction. The opposite of laminar is turbulent, where the fluid flows in rather violent manners as shown here. You have probably heard the pilot warn you of incoming turbulence and ask the passengers to fasten their seat belts. When you hear that, you know it is not going to be a smooth flight. Indeed, in turbulence, the molecules that form the fluid body crosses one another's path in rather chaotic manner. Sometimes you can see both laminar and turbulent motion being exhibited at the same time, such as the flow of the smoke from jaws or incense sticks. By the way, when you see smoke, you are not seeing the air. Air is colorless. Instead, you are seeing the ashes particles which are byproducts of the burnt sticks. However, these ashes float in the air in accordance to the air current that carries them, and hence you can visualize the airflow. The airflow nearer to the sticks is laminar, but further away, interaction with environment causes the flow to turn turbulent. Anyway, back to the main discussion. An ideal fluid is incompressible and laminar. Now let's say we have an ideal fluid flowing down a pipe as shown here. The pipe cross-sectional area may not necessarily be uniform throughout. It could narrow down in some parts or widen up in the other parts, but it has no hole so that fluid can only flow in from one side and flow out from the other. Then the amount of fluid that flows into the pipe has to be equal to the amount of fluid that flows out of the pipe within the same period of time. This is because there will not be any accumulation of fluid inside the pipe from compression. Remember that an ideal fluid is incompressible. Water is far from ideal, but let's assume it is an ideal fluid. If 1 liter of water flows into one end of the pipe in 1 minute, then within the same minute, 1 liter of water has to flow out from the other end. The outflowing water is being pushed out by the inflowing water, and there is nowhere else the water inside the pipe could go but through the other end. For that reason, we can write down the following equation. Delta V1 over T is equal to delta V2 over T, where delta V1 refers to the volume of inflowing water, delta V2 the volume of outflowing water, and T the period, which is the same for both sides of the equation. But delta V1 can be thought of the waterfront having cross-sectional area A1 flowing over the distance delta S1 into the pipe, and as a result, a waterfront of cross-sectional area A2 has to flow over the distance delta S2 before being ejected out of the pipe. As a matter of fact, this process does not only happen to the waterfront on both ends, but also to all waterfronts throughout the pipe, each having different cross-sectional area and traveled over different distance delta S. By the way, please be mindful that A2 could be different from A1 because, I said earlier, the pipe cross-sectional area may not necessarily be uniform throughout. Immediately, we should notice that waterfront with smaller cross-sectional area will have to flow over longer distance delta S in order to keep the volume delta V, which is the product of the cross-sectional area A with the distance delta S, equal on both sides of the equation. If we now recollect the term delta S over T and recall that it actually refers to the speed of the traveling waterfront, we thus end up with what is called a continuity equation. A1 times V1 is equal to A2 times V2. Please take note that it is a small case V in reference to speed, which has to be distinguished from capital V for volume. So as shown in this simulation, the red dot indicates the particles or molecules that form the fluid body. Across a uniform pipe, the fluid will flow with uniform speed. But if the pipe has different cross-sectional area, we can change the shape of the pipe by playing with these handles. So over here I widen up the pipe. And over there I narrow down the pipe. And now you see the particles are no longer traveling at the same speed. At the section where the pipe is widening up, the flow is slowing down. And at the section where the pipe is narrowing down, the flow is speeding up. Yet if we ever consider two different sections along the pipe of which volumes are the same, then within these volumes there is always the same amount of fluid inside. Not just the amount of fluid within the same amount of volumetric section of the pipe is conserved. Energy will also have to be conserved, or to be more exact, since pushing the fluid from one end of the pipe to another requires the presence of force throughout the process, the relation between the change in mechanical energy and work done has to fulfill the following equation. If you are wondering where this equation comes from, well, it comes from the work energy theorem as discussed in lecture 6.1. But now we have the delta U term, which is the change in gravitational potential energy, because the two ends of the pipe are not only having different cross-sectional area, but they are also located at different heights as shown here. The difference in kinetic energy comes because of the difference in speed between the two ends of the pipe due to the difference in the cross-sectional area. We just discussed this in the previous slide. We can thus write the difference in kinetic energy between the outflowing and inflowing fluid as such. Notice that for a reason which will be made clear soon, I write the mass as density ρ times the volume segment of the fluid. Similarly, the difference in potential energy between the outflowing and incoming fluid is given by this. I think this should be pretty straightforward. How about work? What is the work done to carry the volume segment delta V from the bottom end to the top end of the pipe? To compute this, we should first be mindful that to do so, presence of force is required. External force is required to push this volume segment up, for if we leave nature takes its course, there is nowhere delta V could go up by itself. This pushing force comes in the form of pressure P1 at the bottom end of the pipe. The pressure P1 over area A1 gives us the force F1. The force F1 pushes the water front over the distance delta S1, and the work done by F1 is given by F1 times delta S1. But that's not all, because at the other end of the pipe, fluid is gushing out. It also experiences a force F2. This is a force that comes from the external pressure P2, trying to hold the fluid back within the pipe. So the force F2 is pointing opposite to the motion of the fluid. This implies that the work done by F2 is negative F2 times delta S2. Thus the net work done on the volume segment delta V is given as such. We can then recast this equation in terms of pressure times area, and recollect the term area times delta S as the volume delta V, which is the same for both terms. The last step is to put everything together, cancel the common terms, and rearrange the remaining terms, such that one side contains all the terms pertaining to the inflowing fluid and the other contains all the terms pertaining to the outflowing fluid. This final equation is what known as Bernoulli principle or Bernoulli equation, named after a German mathematician cum physicist Johann Bernoulli, who was Isaac Newton's contemporary. The principle relates pressure to the speed or kinetic energy as well as relative position or potential energy of the fluid throughout the pipe. In particular, if we eliminate the height factor and simply consider a horizontal pipe, but having different cross-sectional area as shown here, as we discussed earlier, the section whereby the pipe is narrowing down causes the flow to speed up. However, Bernoulli principle says that when the flow speeds up, the pressure in that section will have to decrease because the sum of the pressure and the 1/2 ρ V square has to be conserved along the pipe. This decrease in pressure is then signified by the difference in the height of the fluid column, in accordance to the hydrostatic pressure equation. If we think of this the other way around, by measuring the difference in the height of the fluid column, we can actually find out the speed of the fluid flowing in the pipe. This contraption, which is called venturimeter by the way, gives us an indirect way to measure the flow speed of a fluid. For more application of venturimeter, you may find out more from the Wikipedia link.